processes. So milling cutter, but before that we'll see the brief information regarding milling cutter. Milling cutters are cutting tools typically used in milling machines or machining centers, and occasionally in other it is called as machine tools. They remove material by their movement within the machine or directly from the cutter's shape. A variety of grooves, slots, and pockets in the workpiece may be produced from a variety of tool bits. A common tool bit types are square end cutters, ball end cutters, T-slot cutters, and shell mills. Square end cutters can mill square slot pockets and edges. Ball end cutters mill radius slots or fillets. T-slot cutters mill exactly that T-shaped slots. Shell and cutters are used for large flat surfaces and for angle cuts. These are variations of these tool types as well. There are four critical angles of each cutting tool: end cutting edge angle, axial relief angle, radial relief angle, and radial rake angle. Depending on the material being milled and what task should be performed, different tool types and geometry may be used. For instance, when milling a material like aluminum, it may be advantageous to use a tool with very deep polished flutes and a very sharp cutting edge. When machining a tough material such as stainless steel, however, shallow fluids and the square of cutting edge will optimize material removal and tool life. A wide variety of materials are used to produce the cutting tools. Carbide inserts are the most common because they are good for high production milling. High speed steel is commonly used when a special tool shape is needed, not usually used for high production processes. Ceramic inserts are typically used in high speed machining with high production. Diamond inserts are typically used on products that require tight tolerances, typically consisting of high surface qualities, that is in non-ferrous or non-metallic materials. In the early 1990s, use of coatings to reduce wear and friction became more common. So most of the coatings are referred to by their chemical composition, such as tin. Tin has a basic yellowish coating and that has fallen out of wide use. Okay, so advances in individual coatings are being made. However, with coatings such as amorphous diamond and nanocomposite PVD coatings beginning to be seen at high-end shops. Now let us see the types of milling cutter. So arbor type of milling cutter, in that there are plain milling, side milling, form milling, fly cutter, and second main classification, that is shank type of milling cutter, having end mill inserted to T slot and fly cutter. So in plain milling, these ones are widely used, and cylinder or high-speed steel with tool teeth on periphery. It used to produce flat surfaces. It has several types, that is light duty helical, heavy duty, high helix. Now next, that is side milling. Comparatively narrow cylindrical milling cutters with teeth on each side and on periphery. It is used for cutting slots and for face and straddle milling operations. Free cutting action at high speeds and feeds. It is suited for milling deep and narrow slots. Now next, that is form milling. So it incorporates exact shape of part to be produced. It is useful for production of small parts, each tooth in identically in shape, and it is sharpened by grinding tooth face, and it is important to maintain original rake but these are difficult to resharpen. So such type of formed cutters are there: concave shape, convex shape, and gear tooth. Okay. So next, that is angular cutter. These teeth neither parallel nor perpendicular to cutting axis. It is used for milling angular surfaces for grooves, serrations, chamfers, and remote teeth. These are divided into two groups, that is single angle milling cutters and double angle milling cutters. So this is called as single angle milling cutters. Teeth on angular surface may or may not have teeth on flat, and its angle is 45 degree to 60 degree. And next, that is second group, that is double angle milling cutter. Two intersecting angular surfaces with cutting edge on both equal angles on both sides of the line at right angle to axis. Now next, that is fly cutter. Single pointed, it is a single pointed cutting tool with cutting end ground to desired shape, mounted in special adapter or arbor. Fine feed must be used. It is used in experimental work instead of a specially sharpened cutter. End mill, cutting teeth on end as well as periphery, and it is fitted to spindle by suitable adapter. And end mill has two types: solid end mill shank and cutter integral, where smaller with either straight or helical flutes, and another has two flutes or four flutes. And second type is shell end mill with separate shank. Now next, that is inserted tooth. Only such cutters are made from a single piece of tool steel have seen so far considered. In large cutters, however, the cost of the steel becomes an important item, and there is the ever present danger of losing a large amount of labor. So, courtesy of Baker Milling Machine Company, Hyde Park, Massachusetts, by breakage when hardening. To make an economical serviceable cutter of large size, it is customary to use a cast iron body with inserted tool steel teeth. There are several different methods of inserting and holding these teeth. Usually, when the inserted tooth is in the form of a blade, they are held by taper pins or screws. These blades are renewable, the cast iron body being used many times. Another form of inserted tooth cutter consists of round hardened steel pins driven into holes in a cast iron body. This cutter is also permanent in form. So, as you can see in figure, broken teeth cannot be replaced, and when the teeth are worn almost down to the body, the whole cutter is thrown away. So next, that is shell type end mill. Paste milling cutters under 6 inch, and it has solid multiple tooth cutters with teeth on face and periphery. It held on stub arbor. Okay, it may be threaded or use key in shank to drive cutter. Next is T-slot. It is used to cut wide horizontal grooves at bottom of T-slot. After narrow vertical grooves machined with end mill or side milling cutter. Okay, that means after using end mill cutter, these T-slot can be performed. Consist of small side milling cutter with teeth on both sides and integral shank for mounting. Next is fly cutter. It is single pointed cutting tool with cutting end group ground to desired shape. It is mounted on special adapter or hardware, and fine feed must be used. It is used in experimental work instead of a specially shaped cutter. So these are the parts and the functions: the teeth, helix angle, center cutting, shank. Okay, these are the parts and their functions are given over here. Now next we are going to see the dividing head, sorry, indexing. So indexing is an operation by dividing the periphery of a piece of work into any number of equal parts, accomplished by dividing her head or index head. So here you can see the principle or mechanism of dividing head. So here you can see the main spindle which drives the workpiece. Main spindle drives the workpiece. Index plate is having holes with crank and pin. Index crank drives spindle through a worm gear. Worm gear has 40 teeth. For one rotation of workpiece we need 40 revolutions of index crank. So here index plate is there. It is equispaced holes around various circles. Normally it is having the company Brown and Sharp company. And it has 3 plates. First plate is having 15 whole circles, 16, 17, 18, 19, 20 whole circles, and second plate is having 21, 23, 27, 29, 31, 33 whole circles, and third plate is having 37, 39, 41, 43 to 47, 49 whole circles in the third plate. So here you can see the index plate number 1, which is having the 15, 16, 17, 18, 19, 20 whole circles, and further here it is, you can see the index plate that you are seeing over here. Next, that is universal dividing head. It is used for all forms of indexing. It is used for setting work in vertical, horizontal, or in inclined position relative to table surface, for turning workpiece periodically through a given angle to impact indexing movement, and for imparting continuous rotary motion to workpiece for milling helical grooves. So methods of indexing are simple indexing, compound indexing, differential indexing. In simple indexing, it is using any one of the indexing plate in conjunction with worm. To find index crank movement, the formula is 40 upon n. N is nothing but number of divisions required. So milling of gear with 20 teeth is there, then n is equal to 20, then index crank movement is equal to 40 upon 20. So index crank movement is 2 whole number. That means index crank is to be rotated through 2 complete turns. And if the gear is with 30 teeth, then index crank movement is 40 is equal to 40 upon 30. Then it has to one complete turn of crank and additional 1/3 of a turn. For obtaining additional 1/3 turn, select plate. Okay, so in such a way we can do the indexing. And for compound indexing, to separate movements, to separate movement of index crank in different whole circles of one index plate to obtain crank movement, not obtainable by simple indexing. Okay, so here two movements, one of index crank as in simple indexing, second of index plate after locking with plunger. So in this first, that is crank pin is rotated through required number of spaces in one of the whole circles of index plate and crank pin is engaged. And second movement, removing rear lock pin and rotating plate together with index crank forward or backward through calculated number of spaces of another whole circle, and then lock pin is engaged. So there are some rules for compound indexing. This is the formula: 40 upon n is equal to n1 upon small n1 upon capital N1. plus and minus, plus or minus small n upon capital N2. So in this, n is nothing but capital N is number of divisions required, capital N1 is whole circle used by crank pin, capital N2 is whole circle used by lock pin, small n1 is whole spaces moved by crank pin in n1 whole circle, n2 is whole spaces moved by crank pin in n2 whole circle. Okay, now let us see one example. Index 69 divisions by compounding indexing. So we are going to put this 69 into the formula. Now resolve first into two factors the number of divisions required. Let us say 23 and 3. Choose at random whole circles, index circles, say 23 and 33. Subtract whole number of one circle from another and then factor the difference 2 into 5. Place factor of divisions required and factor of difference above horizontal line, and next factor the numbers of turns of crank required for one revolution of spindle and also factors of whole circles. Place these factors below the line so you will get such thing. Okay, so now cancel common factors above and below the line. So all factors you can see 23, 23, 3, 3, 2, 2. So all factors above can be cancelled. So whole circles 23 and 33 can be used. So n1 is equal to 23, n2 is equal to 33. If factors above line cannot be cancelled completely, then two other circles should be chosen for trial calculations. Okay. Factors which remain uncancelled below lines are multiplied to obtain spaces in whole circle to be moved by two indexing movement. That is, 44 is the number of whole spaces to be moved for indexing. So index crank should be moved by 21 holes in 23 whole circles in forward direction, and then the plate and the crank together by 11 holes in 33 whole circle in backward direction. Okay, now next, that is differential indexing. It required division is if required division is obtained by combination of two movements, movement of index similar to simple indexing and simultaneous movement of a index plate when crank is turned. So here you can see lock pin is disengaged with index plate, which is screwed to sleeve meter gear is fastened to other ends of sleeve. Index plate, sleeve and meter are free to rotate on worm shaft. Meter gear meshes with another meter gear on shaft. Tail end of spindle a stud. Okay. Now change gear may be mounted between stud and shaft. Gear on spindle is driving gear and gear on shaft 16 is driven gear. Change gear then to may be simple or compounding. So here this differential indexing is not that much important. That means the question will not be asked in the exam, but still we have seen. Okay, let us see the further. So gear ratio, this is the rule for differential indexing: a minus n into 40 upon a. In that, a is selected number which can be indexed by plain indexing and number is approximately equal to n. N is nothing but the required number of divisions to be indexed. In gear ratio so calculated, numerators of friction indicates driving gears on index head spindle and denominator indicates driven gears on index plates. Index crank moment is equal to 40 upon A. Index crank will have to be moved by an amount 40 upon A for n number of complete division of work, and index crank should be moved in same direction or opposite to each other depending on type of gearing ratio and selected number is chosen. If A minus N is positive, plate must rotate in same direction as crank, and if A minus is negative, the index plate must rotate in direction opposite to that of a crank. To achieve these conditions, number of idlers used depends upon. Okay, now let us see directly the example index 83 division. So first find out whether crank index crank can be indexed by plane indexing or not. So formula is 40 upon n. Since there is no plate with 83 number of holes number, so it cannot be indexed by plane indexing. Now as A is equal to 80, let us take A 86. So 86 is near to 83 and can be indexed by plane indexing. So gear ratio, this is what we kept in the formula, and we got this. Now let us see, therefore the driver gears are 72 and 40 and driven gears are 24 and 86, and this is what the index crank moment 40 upon 86, which is equal to 20 upon 43. So for complete indexing, index crank will be have to be moved by 20 holes in 43 hole circles, as A minus N, that is 86 minus 83 equal to 3, is positive and gearing ratio is compound, so there is no requirement of a idler. So next we are going to see the broaching. So these are the basic principles of broaching. It is a machining process for removal of a layer of material of desired width and depth, usually in one stroke by a slender rod or bar type cutter having a series of cutting edges with gradually increased protrusion, as you can see in figure which comes here. It is in shaping, attaining full depth requires a number of strokers to remove the material in thin layers step by step by gradually infeeding the single point cutting tool. In figure B you can see, whereas broaching enables remove the whole material in one stroke only by the gradually rising teeth of the cutter called a broach. The amount of tooth rise between the successive teeth of the broach is equal to the feed given in shaping. Okay, so here you can see in shaping we give so many cuts, but in broaching just you are supposed to do one stroke and you will get the required depth. So here you can see the next is the basic principle of broaching. So this is vertical push, it is inserted into the workpiece, and this is the horizontal pull. This is pull to the left side to achieve this much required hole. Okay, this is the geometry of broach tool. Here you can see the pitch, shank length. So the different types of broaches and their applications. So broaching is getting more and more widely used wherever feasible. For high productivity as well as product quality, various types of broaches have been developed and are used for wide range of applications. So broaches can be broadly classified in several aspects such as internal broaching or external broaching, push type or pull type, ordinary cut or progressive type, solid sectional or modular type, profile sharpened or form relieved type. So here internal broaching tools and their applications, which includes internal keyway, splines, non-circular holes, internal slots. Here you can see. Okay, so these are the broaches are used to get such shape. Okay, this is what the internal broaching is there. Now let us see the next, external broaching. So external surface broaching competes with milling, shaping and planing, and wherever feasible this process outperforms in respect to productivity and product quality, and this may be of both pull type and push type. So main applications of the external broachings are surfacing flat peripheral contour surfaces, grooves, slots, keyways, etc. on through the outer surface of object, and also for external splines of having different forms, and the teeth of external spur gears or gear sectors. Okay, so let us see next the pull type and push type broaches. Pull type broach is subject to tensile force, which maintains alignments and prevents buckling. Pull type broaches are made as long as single piece, and these are widely used for internal broaching, and push type broaching are shorter in length to avoid buckling and made in segment. Push broaches are used for external broaching, preferably requiring light cuts and small depth of material removal. So here ordinary cut and progressive type broach is there. So here you can see the solid sectional and model type broach. Now these are the types of broaching machine according to purpose of use: general purpose, single purpose, special purpose, and according to nature of work: internal broaching, external broaching, and according to configuration: horizontal, vertical, according to number of slides or stations: single station type, multi-station type, indexing type, and according to tool or work motion: intermittent type and continuous type. Now next we are going to see the planer and boring machine. So here you can see the planer. This is the difference between shaper and planer. Planer types: boring, which we have seen. Okay, so boring, we know that it is a process of producing circular internal profiles on a hole made by drilling or another processes. It uses single point cutting tool called a boring bar. In boring, the boring bar can be rotated or the work part can be rotated. Machine tools which rotate the boring bar against a stationary workpiece are called boring machines. Also boring mills also. Borings can be accomplished on a turning machines with a stationary bar position in the door post and rotating workpiece held in the lathe chuck. Okay, so this is what the cutting conditions in boring. Now that is the, let us see the types of boring machine: horizontal and vertical boring machine. Now next we are going to see the MCQ. So here we are going to see the MCQ on the first unit. So let us see one by one. I will directly say the answer instead of saying all the options. I will tell only the correct answer. In metal machining, the zone where the heat is generated due to friction between the moving chip and the tool face is called a friction zone. Option A, friction zone. Now, second question. In determining the various forces on the chip, Merchant assumed that the here the option D is correct. That means all of the three options sentence are correct. Okay, now let us see the next question. In machining metals, surface roughness is due to and the answer is option D. All three sentences are correct. Okay, so question 3 D option is correct. Now the question 4, the tool life decreases as the cutting speed increases. Okay, as cutting speed increases, tool life decreases. Now next, in the relation Vt raised to n is equal to C, the value of n for high speed tool varies from 0.25 to 0.40. So option is B, disagree. Okay, now negative rakes are used for all these, that is for carbide tools, heavy loads, harder materials. Now option C, which statement is correct about nose radius? That both the statements are correct, option A and option B. Okay, so C option is correct for the question 7. Now 8th question, in order to achieve a specific surface finish in single point turning, the most important factor to be controlled is option C, feed. Now next, the tool life is said to be over if here the option D is correct, that means all of the above. Okay, so next question, continuous chips with built-up edge are formed during machining of ductile materials. For question 10, option B is correct, ductile metals. Now next question, the rate of removing metal is increased by increasing the depth of cut. Okay, as depth increases, the removing metal is also increases. Now 12th, the tool life is dependent on cutting speed. Okay, now next, the factor sum of cutting velocity and chip velocity is equal to shear velocity. So option A is correct. Next question, in an orthogonal cutting, the depth of cut is halved and the feed rate is double if the chip thickness ratio is unaffected with the changed cutting condition. The actual chip thickness will be doubled. 15th question, the spindle cutting energy used for establishing the machinability of the metal depends upon the all these three factors. Okay, option D is correct. Which of the following parameters govern the value of shear angle in continuous chip formation? So here also all of these, option D is there for question number 16. 17, the shear velocity is the velocity of, here none of this is there for question number 17. So for 18, in metal machining, the zone where the minimum heat is generated due to the plastic deformation of metal is called as the shear zone. A better machinable metal is one which gives lower chip tool contact area and larger shear angle. Okay, so for question number 19, option A is correct. Now question number 20, the correct sequence. Okay, so here the option C is correct, cutting speed, feed rate and depth of cut. Now Next question, that is, the cutting fluid mostly used for machining steel is soluble oil. Okay, the lip angle is the angle between the tool face and the ground end surface of flank. So next question, small nose radius results in excessive stress concentration and greater heat generation. As the next question, as the cutting speed increases, the cutting tool forces decreases. Next question, crater wear leads to, here D option is there, that means it leads the above three effects. Okay, so 26 number question, the relation between the tool life in minutes and cutting speed in meter per minute is depends upon the tool and workpiece. Okay, so the correct answer is option B, Vt raised to n equal to C. The tool life is measured by the all these factors. Also for 27 number question, option D is correct. 28, crater wear is mainly due to the phenomena known as diffusion of metals. Flank wear depends upon the amount and distribution of hard constituents in the work material. And next question, the tool may fail due to, the option is option D, all of these. Now next, the factor considered for evaluation of machinability is, here again the option D is there, all of these. Now next question, in machining metal, cutting force at the cutting edge is measured by, okay, that is tool dynamometer or dynamometer, option B. Okay, in American Standard Association system, if the tool nomenclature is 8-6-5-5-10-15-2 mm, then the side rake angle will be 6. Okay, option B is there. Now in oblique cutting of metals, the cutting edge of the tool is here inclined at an angle less than 90 degree to the direction of tool travel. Now next question, cutting fluids are used to, the option is D, all of this. Last question, tool life in orthogonal cutting is less than the tool life in oblique cutting. Okay, so here today we are going to stop over here. Thank you.